So in this video I'm going to talk about the Biot-Savart law, and this is covered in chapter 30-4 and 30-5 of the textbook. Alright, so we've talked about magnetic forces, we've talked about magnetic fields, but now we can figure out how do you actually calculate what the magnetic field is. And that's where the Biot-Savart law comes in. So the magnetic field due to a single moving charged particle, we can calculate it. So remember, capital B stands for the magnetic field. So we have a constant out here in front, mu naught over 4 pi. So it depends on the charge. It depends on V, the velocity of this charged particle, and the location R. So now remember this V cross R, so we're multiplying two vectors, and remember this is called the cross product. So in the cross product, if you remember how it works, it depends on the directions and it produces a vector. So if I want to know the magnitude of this, I can take this as V times R times the sine of the angle in between them, which is where this equation on the right hand side comes from. So mu naught is just a constant, so similar to what we had with epsilon naught when we were dealing with electrostatics. So the value is 4 pi times 10 to the minus 7 Tesla meters per amp. And yeah, you could ask the question why mu naught has a 4 pi on it, and because then we divide by a 4 pi, and I guess it just boils down to where you want to throw your factors of pi when you're writing these magnetic field equations. So the units of magnetic field are the Tesla, or the SI unit, and the Tesla is a Newton second per Coulomb per meter, or you could also write it as a Newton per amp per meter. So another common unit of magnetic field is something called a Gauss. So a Gauss is actually 10 to the minus 4 Tesla, and the reason why you use Gauss quite a lot is because the Earth's magnetic field on the surface is roughly on the order of a few Gauss. So the magnetic field is also an inverse square law, just like the electrostatic force and gravity, right? So it goes as r squared, or well, there's an r cubed on the one over on the left here, but we've got an r up here on the top, so it's effectively like r squared. So the direction, of course, is more complicated because we have this pesky cross product. Okay, so that's if we have a single charged particle. So what if we have a current? Well, a current is just a bunch of moving charged particles. So if we look at so let's say we have a wire, so a current traveling through a wire, and we look at some small infinitesimal section of this wire that we'll call dl. So the contribution to the magnetic field from that little element of current, dB, is, well, it depends on the current, it depends on the length, dl, and we have to do this cross product with the position vector r. So we want to know what's the magnetic field at point P, so then we need to take this vector r, which is just the distance from the particular current element that we're interested in. Okay, so if we do this as the magnitude, right, we can trade the cross product for a sine here. So I sine phi over r squared dl. So then, of course, to actually figure this out, then we have to integrate. So we integrate over the length of the wire to get the total field. Now, however, like a lot of these integrals, so remember when we were dealing with electric fields and electric potentials, there was sort of a limited number of situations where we could actually do these integrals, and it's the same thing here with currents and finding magnetic fields. So there's really a limited number of cases where you can get an integral that we could actually do. So now we can look at some of these special cases. So for example, for a long straight wire, if you're on the axis, so we've got a current traveling to the right along this wire, and we're some distance away from the center of this thing. So the magnetic field is mu naught I over 2 pi r, and we've got this factor L over L squared plus 4r squared square root. And we're going to look at some of these in more detail in class. So now if I have an infinitely long or very, very long straight wire, it actually ends up being pretty simple. So the magnitude of the field is mu naught I over 2 pi r. Remember the direction of these fields, so these are just concentric circles centered on the wire itself. So if I have a loop of current, so now instead of a straight wire, I take that wire and loop it into a circle. And of course there's something that's providing the current to begin with, but we're not going to worry too much about that. And again, if you're on the axis, you get a more complicated expression for the magnetic field. And in general, similar to what we had with the electric field, so we have these few special cases, And generally, right, you use these special cases to break down more complicated current shapes into the simpler ones. And then you just use superposition and you add together the contributions from each of the individual simpler cases.